Dear audience, we are pleased to introduce our work presented at CVPR 2025 towards Long Horizon Vision Language Navigation, Platform, Benchmark, and Method. First, I would like to introduce the current state of research in embodied navigation. As shown in the image on the right, embodied navigation tasks can generally be categorized into three types: object localization navigation, demand-driven navigation, and vision language navigation. In object localization navigation, the agent receives an instruction that describes the location of a target object in detail. The agent must explore the environment, approach, and locate the object accordingly. In demand-driven navigation, the agent is given a human need and must infer which object can fulfill that need and then find it in the environment. Vision language navigation, the most traditional type, has received considerable attention, primarily driven by the R2R benchmark. In this task, the agent receives a step-by-step instruction such as moving forward to a location, turning at a specific spot, and continuing until reaching the destination. However, all of these tasks suffer from several limitations. First, the task definitions are relatively simple and do not align well with real-world requirements. For instance, in vision language navigation, it is unrealistic to expect humans to provide such detailed step-by-step instructions in everyday scenarios. Second, there is a lack of scene diversity. Most benchmarks contain fewer than 100 scenes, and the scenes themselves are relatively small in scale, which limits the generalization ability of trained agents. Lastly, there is a lack of evaluation regarding the agent's understanding of the task. It's unclear whether agents truly comprehend natural language instructions or how those instructions influence decision-making. To address these limitations, we propose a new embodied navigation task, Long Horizon Vision Language Navigation. As shown on the far right, we design complex navigation tasks that consist of multiple interrelated subgoals. For example, the agent may be instructed to take the towel in bathroom to the kitchen island in kitchen, then grab the teapot and release it on the coffee table in the living room. There are 4 navigation target: towel, kitchen island, teacup, and coffee table. They are logically connected. The agent must complete each subtask in sequence, understand the current progress, and adapt its strategy in real time. This setup requires agents to possess longer-term memory capabilities and a deeper understanding of natural language instructions. Based on the design of the LHVLN task, we propose a new set of evaluation metrics. Traditional embodied navigation metrics, such as success rate, success weighted by path length, and navigation error, are designed to assess the performance of single-goal tasks. However, these metrics are not well suited for LHVLN tasks, which involve multiple interrelated subgoals. To address this, we first introduce independent success rate, which independently calculates the success rate for each subtask. More importantly, we propose 2 core metrics specifically tailored for LHVLN: conditional success rate and CSR weighted by ground truth. These metrics are designed to evaluate whether the agent truly understands the complex task and completes it accurately. The diagram on the right illustrates how CSR is computed. Suppose the agent is given a complex instruction consisting of 4 sub-goals, and it is currently at the second step, successfully locating the kitchen island. At this point, there are 2 scenarios. 1. The agent has already retrieved the towel from the bathroom as required. 2. The agent has not retrieved the towel, even though the instruction clearly states that the towel must be brought to the kitchen island. In the second scenario, finding the kitchen island alone is not sufficient as it fails to fulfill the instruction's intent. Therefore, the CSR metric applies a penalty to this subtask score, a decay factor of 1/n, where n is the total number of subtasks. If all prior dependencies have been fulfilled, no penalty is applied. This cascading penalty mechanism continues throughout the task, meaning the failure to complete earlier subgoals will negatively impact the score of subsequent subtasks. CGT builds on CSR by incorporating a weight for each subtask based on the length of its navigation trajectory. This reflects the idea that more difficult subtasks, typically associated with longer paths, should have a greater impact on the overall performance score. Together, these metrics offer a more comprehensive and realistic evaluation of agent performance in long horizon, language-guided navigation tasks. We also designed an automated task generation framework called NavGen, which consists of two main components: forward complex task generation and trajectory recording, reverse trajectory decomposition, and step-by-step task generation. In the forward process, we begin by sampling from a pool of scenes and a pool of robot configurations. Based on constraints such as semantic relevance, spatial distance, and task format, we generate base LHVL and task configurations along with their corresponding subgoal decompositions. These task configurations are then deployed in a simulator. Using either navigation models or expert agents, we generate trajectories and collect observations to build a trajectory dataset. In the reverse process, we apply a trajectory segmentation algorithm to decompose the collected trajectories into action segments, each labeled with a specific type of movement based on action distributions. For each segment, we use a vision-based annotation model to assign semantic labels. These action and semantic labels are then fed, in sequential order, into a large language model, which generates a step-by-step natural language navigation instruction corresponding to the original trajectory. This bidirectional task generation framework allows us to automatically and efficiently create a diverse set of navigation tasks. It enhances task richness and supports multi-instruction annotations for the same trajectory, enabling more comprehensive evaluation of navigation models. The final statistics of our generated dataset are as follows. We collected data from two types of robot perspectives, covering 216 complex, continuous scenes and 3,260 LHVLN tasks along with their corresponding step-by-step instructions. On average, each task consists of 150 action steps. Compared to datasets such as VLNC, Behavior 1K, and FAO, ours offers advantages in both scale and complexity. The proportion of tasks from the two robot types is roughly equal, and most complex tasks involve 2 or 3 goals. For tasks with different numbers of goals, the average number of action steps per subtask is around 60. As the number of goals increases, the agent tends to cross more floors, the backtracking rate rises, and goals are more likely to appear in the same area. For the LHVLN task, we designed a navigation model called MGDN. The core architecture is a large model-based multimodal fusion embedding framework. RGB observations from 3 directions are treated as action candidates, which are encoded and fused using a VIT, then embedded into the language space and input into a large language model. The fine-tuned output of the large model is passed through a multi-layer perceptron to select atomic actions. The key innovation of the model lies into components: thinking before acting and forgetting after acting. For thinking before acting, we utilize GPT-4 to interpret and reflect on the current progress and generate prompts for the next action. For forgetting after acting, we apply a self-supervised dynamic forgetting algorithm, where memory segments are average pooled to create a blurring effect in memory, reducing the influence of outdated information. Next, we will look into the details of these two components. First is thinking before acting. Thinking before acting is essentially a process of generating a chain of thought. The agent performs step-by-step reasoning based on instruction understanding, task localization, and chain of thought generation. During instruction understanding, the agent forms an overall understanding of the task instructions, identifying the sequence of navigation subtasks it needs to complete. During task localization, the agent uses past key memory observations to confirm the current task progress and the upcoming goal. In the chain of thought generation phase, the agent generates a complete chain of thought based on the previous 2 phases and incorporates it as a prompt into the multimodal embedding. For forgetting after acting, there are 2 key elements: H and C. H represents the memory primitive at a certain step, specifically the fused visual observation encoding corresponding to that action step, while C is the confidence vector, derived from the output of the large model at each action step. Memory primitives and confidence vectors are 1-to-1 matched. The agent maintains a memory sequence with a maximum length. When the accumulated memory length exceeds this limit, forgetting is triggered. Each confidence vector and its adjacent elements are average pooled, and the entropy of each pooled result is calculated. The confidence vector with the lowest entropy and its corresponding memory primitive are selected as the forgetting elements. Through average pooling, the sequence length is reduced by 1, and the new memory element is added, thus maintaining the memory sequence. Next are our experimental results. Our experiments aim to address 3 main questions. First, we find that existing navigation models struggle to understand and complete multi-stage complex tasks under limited information. Each model's success rate is 0, indicating that none of them can effectively complete the tasks. Combining complex task decomposition with single-stage navigation models can improve performance on complex tasks, but this approach lacks a holistic understanding of the task and leads to incomplete and fragmented memory. We integrate GPT-4 with the navigation model Navi LLM, and this combination does show improvements over NavILM alone, but it still underperforms compared to our model. Finally, while longer, multi-stage tasks may seem more challenging overall, the accumulated memory from earlier stages actually aids the model complete subsequent subtasks. We observe that complex tasks with 3 to 4 sub-goals achieve better results than those with 2 to 3 sub-goals. This outcome is due to the memory accumulation mechanism and the characteristics of the tasks themselves. As mentioned in our earlier dataset analysis, with more goals, the agent tends to cross more floors, the backtracking rate increases, and goals are more likely to appear in the same area. A higher backtracking rate means the agent is more likely to encounter key information relevant to later sub-goals during earlier subtasks, which subsequently benefits navigation performance in later stages. Finally, we present a demonstration of an LHVLN task. The agent receives the instruction: take the backpack from the bedroom to the couch in the living room, then retrieve a book from the living room, and is initialized in an unseen environment. The agent needs to understand the instruction and analyze that its first goal is backpack in the bedroom, so it proceeds toward the bedroom to locate the backpack. As shown, it finds the backpack in the corner of the bedroom. After finding the backpack in the bedroom, the agent needs to reassess its current progress and determine that the next navigation goal is the couch in the living room. Once the couch in the living room is found, the agent evaluates the instruction again and identifies that the final task is to find the book in the living room. Alright, that concludes our presentation. If you are interested in our work, feel free to click the link in the video to visit our homepage. Finally, thank you once again for your attention and support.